Hello students, so this is Vaishak here from Evolve Robotics. So as we promised, we are now going to start our tutorial on a real-time operating system. So let me give you an introduction about real-time operating system. So it's a specialized operating system which is designed for embedded systems that require predictable and timely responses to events. Okay, so you know that unlike general purpose operating system like Windows, Mac OS that prioritize user experience, this RTOS focus on guaranteeing a response within specific time frame. Okay, this is crucial for applications where delays can have serious consequences such as industrial control, medical device, avionics, internet of things, etc. And when we use real-time operating system, the process include task scheduling, real-time clock, inter-task communications, device drivers, etc. So this RTOS kernel is responsible for driving the device peripherals. If you need to make communication possible between your application layer and the uh, machine peripheral devices, then you need to include a kernel, integrate a kernel with the operating system. So this kernel is responsible for the communication between our application layer and the hardware. Okay, so talking about FreeRTOS, it's a widely used open source RTOS kernel specifically designed for microcontrollers and small microprocessors, and it is maintained by Amazon Web Services. So it's well known for reliability and ease of use, flexibility, and it's an open source. Also, it has a widely a huge community support in its website. Okay, so FreeRTOS provides the core functionalities of an RTOS, including task scheduling, inter-task communication, timing, and synchronization primitives. So it is more accurately described as a real-time kernel or real-time executive. Okay, in summary, RTOS are essential for embedded systems with strict timing requirements, and FreeRTOS is a popular open source option that offers an easy to use foundation for real time development. So coming back to our program, let me show you how we can configure a project for real-time operating system using Keel IDE, especially for LPC2148 microcontroller. Okay, let's come back to our IDE. um, okay, so I will minimize my camera window. So you can see the Keel IDE now. So in this I have created a small project to blink an LED which is connected to our port 0 of the LPC21 microcontroller, LPC2148 microcontroller. So for that purpose, I am using RTOS, real-time operating system, which is FreeRTOS of Amazon Web Service. So to use FreeRTOS, we have to include this much files here. So I have included my main C source file, which is one RTOS, and after that I have also included this task.c, list.c, queue.c, port.c, etc. in my project, but we are now only going to use this task.h file only. For that you need to include task.c source file, and in that C source file it will call our task.h file also. So in that task.h file, all the API functions which is related to the tasks are defined. So in order to use this API functions which we need to create and manipulate our tasks are defined in this task.h file. So this source file is very much important, and you need to include that source file whenever you are working with the FreeRTOS. Okay, and after that, this list.c and q.c. This q.c we are not going to use in this project, but you may need this list.c. So keep this list.c in your project always. Okay, and also you also need this heap 2.c, which contains the API functions related to manipulating your stack and heap memory. Okay, so it is must that it is important that you have to add this heap source file also in this project. So after that, you need port asm.s in order to control your port. Okay, so other than q.c, all the other source files are very important also. You have to include these files always in your project, even if you are working for a simple LED blinking project. You must need to include these this much files. Okay, so after including these much files, I have the first line, I have included standard library functions of C, and I hope you don't need any explanations for that. After that, I included FreeRTOS.header file, which will configure our FreeRTOS in this key IDE. Okay, after that, include a task.h, which contains all the API function definitions to control and create and control or create and manipulate our task, and allocating the memories, priorities. Also, these vtask scheduler functions are defined in this task.h file. Okay, so I have to include this file. And after that, you can see our main function. In our main function, I'm using this IO0 dir register of LPC2148 and configured its 31st pin as output pin. You can see this unsigned long, which is a typecasting, and I have typecasted this one to unsigned long and shifted 31 times for 31st bit of the IODIR register. So it is set, and that pin is now set as output pin. Okay, so after that, this is an API function which is a xtask created. It is an API function which is defined in our task.c source file. Okay, task.h source file. Okay, so it needs this much arguments. We need to pass this much arguments to that function. So first argument is our task name. It is called LED blinker, and this is our task name. And the second argument is just a descriptive name for our task, and I have given it as LED in double quotes. Okay, and also we have to mention the task stack size. So how much size of memory in stack should we provide for this task, and I have set it as minimal stack size. So this minimal stack size is macros which is already defined in FreeRTOS config.h file. So let's check what is the minimal stack size in FreeRTOS.h file. So let's expand this task.c here. You can see FreeRTOS config.h file. So let me click on that, and coming below, you can see here this is our minimal task size unsigned short. So you have to check the size of unsigned short and multiply it with 90. So this will be the minimal stack size which we mentioned here. Okay, so this much memory, stack memory, is allocated for this LED blinker task. So then the null function, null argument, sorry, this null argument is for if you have any values or variables of, if you have any arguments to pass to that function, you can mention it here. Okay, if you don't have any parameters to pass to the LED blinker function, LED blinker task, you can keep it as null. Okay, so it's just a argument or variable to pass to your task function. So currently we have no arguments to pass, so I have given it as null. And this is a this argument, this place goes for setting the task priority. So you know that idle task priority is always 0. If you have no task, if you have if you are working with without any task, we have no task, then this idle task will be continuously executing in our system. Okay, its priority will be 0. So idle task priority is 0, and our task needs a priority of 2, so I have add 2 with that idle task priority. Okay, and so what's the priority of our LED blinker task? It is 2, so it's a high priority. And this task will, if you have a priority with 1, first this LED blinker task will execute because it has a priority of 2, then only the task with the priority 1 will execute. Okay, so this RTOS gives priority for higher priority task. And after that, this argument is for task handle variable. Okay, if you declare any variable for task handling, and that you can mention that variable here, and you can pass the task base memory address to that variable, then you can use that variable for manipulating this task. Okay, but now I'm not going to use any task handle variables here, so because we are not manipulating this task. This program is just to show you how a RTOS works with a sample example with a blinking an LED. Okay, so after that, our main function of below, we have defined what our function is. Okay, just a definition of our LED blinker function, and we call it as also task. So it's a task we have created here. So this LED blinker task is taking, if there is any variables, any values that it has to receive, then we use this star p. But currently here you can see we have given null, and we are not receiving any values here, but even the program will still execute without any error. So inside the while function, while condition, we have set our first pin to high. So this 31st pin will set to high, and the LED connected to that pin will be lighten up, will blink for a delay of 100. Okay, so after this delay, we have configured our IO0 CLR register of LPC2148 to 1. Okay, the 31st bit of IO0 CLR will set to 1 to clear the bit. Okay, to clear the IO0 set, 31st pin of the IO0 set. So the pin which we have turned on here will be cleared, will be set to low when the program execution reaches here. Okay, because you use IOCLR register of LPC2148 to turn off the 31st pin of the microcontroller, LPC2148 microcontroller, and it will remain in off state till this delay ends. Okay, and after this delay it again goes to here, and it will again start to blink, or this LED will turn on when the program reaches here. And this function is there, we are having only one function, so this RTOS, this CPU will give time for executing this function only. So this function will continuously execute in our project. Okay, so now let me show you how this code works. Let me put this IDE into debug mode, and I will run this code. Then you can see how the pin 31st pin of the port 0 of LPC2148 microcontroller blinks. So let me click on debug option. Okay, and so I'm going to run my code. So you can see in general purpose input output window, which is blinking with a delay of 100. Okay, we have put delay, we task delay as 100, and it is almost 1 second it is taking now. Okay, 1 second, turning on, turning and off. Okay, so the 31st pin of the our micro RPC2148 microcontroller is turning on and off with a delay of 1 second. So this is how our task works. Here you can see that in the int main function we are not calling any functions we created, we are just scheduling using an API function called vtask scheduler, and this vtask scheduler is already defined in task.c file. Okay, so this is how our RTOS works actually. I hope you understand. I hope you understood this basic program. Then we can move on to the next topic. We can dive deeply into real-time operating system in the next lecture. Okay, thank you for watching.